Hello everybody. Today I'm going to be talking about these two blocks right here. I ordered these back in June from a landscaping company and I just had them dropped off last week because I couldn't figure out how to move them here. They dropped them off here. This is not where I want them. What is the point of this? Well, today I'm going to take you through algebraically how to solve for mass of one of these blocks, or for all intensive purposes, weight. Because I want to move these. I don't want these here. This is where they dropped them off, but I need to know if my dolly can physically support the weight, and it has a capacity that is known, okay? So we're gonna go through an algebraic story problem today. And this is a real world application of why that stuff you learned in high school was important. It wasn't just, oh, I don't need to know this stuff. This stuff isn't worth spit. Well, actually it is. Now, some of you, just through real-world experience and practical application, may know how to solve for this already, and that's fine. And there's more than one way to solve maths problems. Okay, but we're going to go through it in a story problem format in order to better facilitate the process. That's why they teach you it that way in high school. It's not something to be afraid of. It really isn't. And you can see the beautiful ripple marks in this, and I love these. Now we are going to model it as a three-dimensional planar object. It's not a cube, it's a 3D rectangle, if you will. We'll just call it that, okay? So it has length, it has width, and it has height. Now I've already measured these. I did it earlier today. These are the results. Here's length, here's width, and this is the height in inches. Don't worry, for those of you that are metric, I am going to convert and switch between the two. It's good for the blood, okay? Because I live in the US and you'd be hard pressed to find a tape measure in metric out here. So I need to convert, all right? And I'm gonna convert those inches into centimeters for the most part, because that's the most practical unit in the metric system, because I need to compute density in order to get mass. Why do I need to do that? Well, the length, width, and height is going to give me my volume, because those of you who know the density equation is density is equal to mass over volume. Well, I don't have the mass and I don't have the density. I can get the volume from this. So what am I going to do about the other two? Well, I need to know the mass because I need to know if this will fit on my dolly. Well, how do I do that? Well, I have to come up with a density. And there are several ways to try to figure out what the density of this rock would be. I am going to use this USGS publication and the standard for Dolomitic Mount Simon sandstone. These blocks are sandstone, but they're really hard. Obviously, they've been cut, transported, knocked, and haven't fallen apart. They're not friable. There's something here holding it together. It could be a calcareous element. It could be silica. I don't know. It doesn't matter. But that's what I'm going to use. So I'm going to use 2.65 grams per centimeter cubed as a density with a porosity of 0.7%. I want to put them back here. And we're going to say, for the sake of argument, that I'm putting them in a cylindrical shaped in-ground pond that holds 800 gallons. And we'll come back to that. That's because I want to do this in a couple bit of sections. In reality, I'm just going to put them back there. But obviously, I can't pick these up and move those. Okay, so say I want to use this dolly. We'll forego how I would get that up there at this point, and obviously this wouldn't hold it. This is just for demonstration purposes. I know how I'm going to move it now because I calculated the mass, and for all intents and purposes that's equal to weight. Now we'll say this holds 250 kilograms, which is roughly about 550 pounds in imperial. Okay, so I need to know if this will support one of those in its weight, so I can move it to my hypothetical 800-gallon pond that would be over here. So let's leave those blocks, pass our hypothetical pond, and go into the geoshed and do some board calculations. Now, before we get started, there's a couple other things I need to mention first. This is just a rough calculation to show you the practical applications of mathematical problems. But it's more than that. I actually do need to move these blocks. I need to know their mass or weight so I can see if I can put them on my dolly and to see if they would fit in my hypothetical pond. Well, you know, like I said, I can calculate a rough volume, but the mass eludes me and the density eludes me, so I'm going to use standards for the Mount Simon. Now, this is just rough, okay? This is just an approximation. I could be off plus or minus 5 kilograms, you know, either way, it doesn't matter, all right? Because I don't think that this block is over 250 kilograms or 500 pounds. It really can't be. It's not quite that big. In order to show you this practical application, I'm going to need to do a lot of stuff on the board here again on the good old trusty dry erase board. But not only do I want you to get how this is done out of this lecture, but I also want you to understand that maths isn't the enemy. It's not, it's a way of thinking. It's like a language. Now, me personally, I am horrible with the written word. I am bad with the English language. I suck at it. But maths I can do. And people argue whether maths was discovered or if it's a language we wrote to describe the natural world. Personally, I think it's discovered to a certain point. But that's a talk for another time, and mathematicians argue about that to no end. But that aside, let's get started here with this problem. Hey everyone, before we get into what's behind me, I am going to set up a story problem for you. Why am I doing that? Well, because we need to be able to pull the relevant information from to see which equations we need to use, because if you're trying to figure out something like the volume of a rectangular cubic object, you don't want to be pulling equations for spheres. That doesn't make any sense. And the story problem puts it in a nice format. You may not agree with the format, but it's one that almost anyone can pull the necessary information from, because we do think in language, and a story problem puts it into language for us. And in this case, this is the story problem we are going to be using. I'll read it to you. It's basically, I have a sandstone block that has a length of 47 3/4 inches, a width of 18 1/8 inches, and a height of 5 5/8 inches. Don't worry, I will put metric conversions up because we're going to use it metric for a reason. The average density of the dolomitic Mount Simon sandstone is 2.69 grams per cubic centimeter, which is roughly equal to 167.9 pounds per cubic foot. Okay, and we pulled that information from the USGS publication. I need to know the mass of this sandstone block in order to know if my cart that holds a known 250 kilograms or approximately 550 pounds is strong enough to hold the sandstone block. I would also like to put it in the pond, which I talked about at the beginning of the video, of the hypothetical pond. I need to know how much water would be displaced because I have an 800 gallon, which is a 3,028 liter capacity pond, and I don't want it to have any overflow. The pond currently has 750 gallons in it, so it's not at full capacity. But I need to know if I put that sandstone block into there with that 750 gallons, is that going to overflow? Because I want to avoid that. So I might have to take water out. So we basically need to answer 3 questions here. Question number 1, we basically need to know the mass of the sandstone block, and that's what we are going to do here. Okay? And then question 2, we need to know the volume of the water that will be displaced when we put this block into our pond. 3 is the porosity thing. You know, I kind of included that porosity at the beginning. Porosity is important because it can affect the weight of our sandstone block, and it was at 0.7%. I need to know if, when I take that into account, if that's going to make our load any less or easier to move. Okay, so we know we need the mass of our block. And here we have density. That's my symbol for density, and it's orange. It'll be color consistent. Is equal to 2.69 grams per centimeter cubed. And my mass is black because it's our unknown. Sandstone block is in black. That's ripples on top of it, those hatch marks. Over our volume, which is blue. Now, our volume is going to take a little bit of work. But before I do that, you can tell that by setting up this problem, because this is a problem given for density and masses in it. This is the appropriate problem because we have density and we can get volume from this, hence the measurements I took earlier in the beginning of the video. But we don't know our mass, so we need to algebraically manipulate this. Well, how are we going to do that? Well, I'm going to show you how to do it with the actual numbers because the units do a little bit of stuff too. But I'm just going to show you how to algebraically manipulate this. Well, anything you do to one side of an equation, you have to do to the other. We want to get this alone, our mass. So what we need to do here, I need to move these a little bit, is we need to get rid of this volume and put it over here. Well, in order to do that, we need to multiply by our volume here. And that will cause the volumes to cancel. And then we will get volume, and I'll put it in blue, over here. And we will be multiplying our volume by our density to get our mass. So the equation we are going to use is going to look something like this. Now I'm going to flip this around so my mass is to the left. It's just a matter of doing this. I mean, you're not algebraically manipulating it, you're just repositioning for your purpose. So it'll actually be M is equal to my volume multiplied by my 2.69 grams per centimeter cubed. And there's a big space here for a reason. You'll see why in a second. So all we've done is move everything from the left to the right. That's just a language thing. It's not an actual algebraic manipulation. But our volume is here. Well, what is our volume? Well, that's why I took those 3 measurements at the beginning of the video. We can't just, there's no one number just to plug in there. So we're going to put the parentheses up because multiplication, remember, can be denoted in several different ways in math. It can be denoted with an X, which is real common. You learned that in grade school. A dot, which is also used. Or you can use parentheses or brackets or something like that. We know how to calculate volume from a rectangular block object like this. It is our volume is our length times our width times our height. And we are doing order of operations here. So we will have to work what's inside the parentheses before we multiply by the outside. We'll just keep that simple, okay? But where do I get my length, width, and height? Well, I did it at the beginning of this video. We took length, width, and height measurements with an actual ruler. And as to which way is length, width, and height is kind of arbitrary. In this case, and in most cases, your length will be referred to as your longest part of an object. And in that case, that was this. This was our length. Now your width is going to be 90 degrees to that along the same plane. So that was my length. My width is right here. That equals my width. Now remember, this is a 3-dimensional object represented as 2, okay? And my height is generally taken as what would be our z-axis. This would be our x-axis, this would be our y-axis, and this would be our z, but we have a specific height there, so we can just extrapolate it, and this is equal to our height. In this case, that's how it was measured. We measured it in inches. For those of you that don't know, the quotations are inches. Now you see things like 47 3/4, and I translated it to centimeters. You can use an online calculator for that, but you're going to have a hard time with this. So what you need to do first is you need to, when you take these fractions, ignore this part. So like, we'll just do one for length because I don't want this to be 30 hours long. So our length is equal to 47 3/4 inches. I'm going to, at present, just ignore this and focus on the 3/4. This fraction is a division problem. 3 divided by 4 is equal to 0.75. Now I take that 0.75 and add it to my 47. So I take this, add it to that, and I get 47.75 inches, which I can convert to centimeters by multiplying by about 2.54. Now remember, units, we don't really bother with units when we do conversions, and that's a talk for another time because it's a factor. And you know, we are changing inches into centimeters by this conversion factor. So we know our units are going to be in centimeters. And that, when we do that, we get the, 123.3 centimeters. Okay, just taking it to one decimal place. I am rounding as I go because it's not going to affect the results that much. But if you're inexperienced with this, you want to hold off on the rounding till the end. Okay, so I've rewritten it, our length, our width, and our height to get rid of the busyness. And according to our order of operations, we multiply everything in here together. All right, now we multiply this together before we do anything else because it's within parentheses and we are doing multiplication. This is still my length, this is still my width, this is still my height. And you see I kind of I rewrote this from that. Look in there, and I'll get into that why in a minute here. But let's do this first. So we multiply all these things together. Feel free to use a calculator. I know when you're younger, you're taught not to use one. You're in like grade school, you don't use a calculator. Well, that's because they're trying to show you the process. That is not math. That is calculation. All right. This is math, what we're going to start doing a little bit. We're getting into math. As you grow up, they will let you use a calculator. Okay. So feel free to do this. Okay. So we multiply all this together. Okay, so you get this incredibly large number when you multiply your length times your width times your height. This is your volume. Don't freak out at the size of the number. It's fine, and we are going to work with it because we can cancel units now. Now, if you remember, my length is in centimeters, my width was in centimeters, my height was in centimeters. Where's this centimeters cubed come from? Where's this cubic centimeter come from? Well, when I multiplied my length times my width times my height, they were all centimeters. So when we multiplied our actual values, we had to do the same here. And a centimeter times a centimeter times a centimeter is still 1 centimeter, but it's also centimeters cubed, because even though we don't write it, there are ones in front of each of these. Okay, so that's where the centimeter cubed comes from, or cubic centimeters. Why does that matter? Well, because you may know mass is going to be in grams or kilograms or pounds or something like that. A measurement of mass, or in this case, weight, essentially. It's not going to be in centimeters cubed. Well, that's where cancellation comes in. That's why I wrote this as a division problem, because even though we don't write this, there's also a number 1 under here. Any number divided by 1 is that number. In this case, it's also 1 cubed, but there's a fraction there, okay? So that means these two units here cancel out, and that'll go with it. So our units have canceled. We still have grams. There was nothing to cancel with grams, and that's what our mass will be in, grams. So stuff's all tied together. So we just multiply these two. And in this case, when we do that, we get this even larger number of 214,638.167 grams. We keep the grams because it didn't cancel. That is our mass. We don't need that top part of the equation anymore. We have our mass. But this is a big, messy number, but we're going to continue to work with it. But you can convert this, and I know a lot of Americans won't understand this unit. First, let's convert this to kilograms. Now, there are 1,000 grams in a kilogram, so a kilogram has more grams in it than a gram has fractions of a kilogram. So what that means is we are going to convert by a factor of 1,000, or divide by 1,000, and that will essentially just move the decimal point to where the comma is, and we will round and get rid of all the other stuff, and we get about 214.6 kilograms. Now the conversion factor for, see how easy metric was? Nice, even, round number, 1,000. But for everybody else so you know, so you can be familiar with how much this actually is, I'm going to convert it to pounds for you. So in order to convert this to pounds, there are about 2.205 pounds in a kilogram. So we're going to multiply by that factor, 2.205. Remember, no units, it's a conversion. So our mass is also equal to about 473.1 pounds. That's approximation because I rounded, but for all practical intents and purposes, it's equal. When you write pounds, it's lb, that is Latin, that is already in plural form. So just so you know, doing that is incorrect because it's already in plural form. So it's just lb. That's just a little tip there for you. So our sandstone block, based off of our density, which we pulled from that USGS chart, is 214.6 kilograms or 473.1 pounds. Now, if you remember the story problem that I set up and my intro part with the dolly, you'll know its capacity is 250 kilograms, which is about 550 pounds. And we have a mass of 214.6 kilograms. So this is greater than our 214.6 kilograms, which is also less than this. So will our dolly support this block? Yes, it will. Okay, that question has been answered. Well, assuming our 2.69 grams per centimeter cube is a good rough estimate for our volume. Well, I actually do know that the 2.69 grams per cubic centimeter is a reasonable approximation. It's actually slightly high, so our weight is probably actually a little less than this. I just want to interject with this part here because I actually did a density test. These flecks of sandstone here are from that other block, which they were both cut from the same quarry, probably side by side. The ripple marks are upside down on the other block, but they look very similar. So I did a density on this, and here is the results. I got 2.64 grams per centimeter cubed, which isn't much less than this. I was within 0.05 grams per cubic centimeter. We're going to just continue with this because it's better to be a little higher than lower on something like this, but it wouldn't affect the values too much anyway. Now for our second question, we need to know if that 750 gallons of water we have in our pool is too much. Anyone who's ever filled a bathtub and gotten in it knows you don't fill that bathtub to the top and then get in it, because if you do, what happens? The water gets all over the floor. Same thing happens to just about any solid object you put in the water. Well, any solid object that's denser than the water anyway, same thing's going to happen. So we have our bathtub essentially filled to 750 gallons, all right? But it's an 800-gallon bathtub or pond, okay? And we already know that the sandstone block will fit in it and the water will totally cover it. We're just going to assume that because I actually did do some very complex equations to calculate the actual volume of a nice pond that would hold that, but we're not going to go into that because if we did, this thing would be 7 hours long. So maybe another time, maybe. This is our capacity, 800 gallons, which is equal to about 3,028.3 liters. We have 750 gallons of water in it, which is about equal to 2,839.1 liters, which leaves us a head space of 50 gallons or about 189.2 liters. And we're just going to get rid of that because I'm going to work with the gallons. I just put the liters there to give you an idea of how much that actually is for those of you who are more tuned to the metric. Because out here, if I was to get a cylindrical pond case like that, it would be in gallons. So, and just so you know, this particular pond would be about 9.1 feet in diameter, which is about 277.7 centimeters, and deep it would be about 1.64 feet or 50 centimeters, okay? Just so you know the size of the pond we're working with here. How do I do this? How do I know how much water is going to be displaced when I set that sandstone block in there? And is that displacement less than 50 gallons? because that's all I've got to work with here. If I get a number greater than 50, I'm going to have to remove water. If I get a number less than 50 gallons, I can just put my sandstone block in there. So in order to get our amount of water, well, that's a volume. So it either has to be like in gallons, like with the 800 gallons or 750 gallons, or in liters, like the 3028 and whatever that other one was. I mean, we could even turn the gallons into quarts or ounces if we really wanted to, but our pond capacity is in gallons, so we should stick with that. Now, I've been using metric to calculate this, and this is why I've been using metric and not just trying to fumble through a bunch of standard units that really have no rhyme and reason. Because as you can see behind me here, I have taken our volume in cubic centimeters and set it equal to milliliters, and it's the same number. Why is that? Here I have cubic centimeters, which is a volume, and here I have milliliters, which is also a volume, but why are these the same? Why are these units identical? Well, those of you who have messed with the metric system for a long time already know the answer to this, and it's one of the beauties of the metric system. It works really well, especially in calculating things really, really fast, especially when you're dealing with different things like volume and mass and density and area and things as such, all right? When you're interchanging, this works better. But the reason why is because 1 cubic centimeter at standard temperature and pressure, what we call STP generally, is equal to 1 milliliter of water. So these two are directly equal to one another at standard temperature and pressure. Now, I'm not going to tell you what that is. You can look it up anywhere. They're equivalents. So I don't need to do any math. All I need to do is change this to this. That's it. Okay, so for clarification, I put our original volume in cubic centimeters as volume, not volume 0 subscript. And this is our volume subscript 1. That's commonly done in math when you're working with very similar concepts like volumes, but you're working with different numbers. Instead of just using X and Y or V and W or something like that. It helps keep it consistent. But anyway, so this is my volume of my sandstone block in milliliters. Okay, so all I need to do with this is convert it into gallons. So, but it will be in gallons. Hello. What's wrong? So, we have a quick interlude. I ignored a certain somebody when I got home, so Sarah comes home. He escapes into the basement and gets spider webs all over him, and now he smells funny. He's going to stay here with me while Sarah goes inside and does something. You know what to do for dinner? Do you know how to do the sausage? Quick interlude here. The interruption with Blackie caused my train of thought to derail. Now, when I actually ran these calculations, I did them correctly. But when I was writing on the board, here I say the conversion factor is for milliliters. It's actually for liters. When I ran the mass, I used liters. But on the board, I wrote milliliters, and I didn't catch it because of the interruption. But it's going to work out. It's on that conversion factor of 0.264172 is for liters. All right, it's still going to get us the answer because when I did it, I did convert the milliliters to liters. I just didn't do it here on the board, and I apologize for that. Sorry about the interruption. You want to do it? Yeah. And the noodles and some of the sauce? Yeah. So he's going to stay in here with me so you might see him. Ridiculous, Blackie. You're out of control. Terrible. So I have my little helper now. But anyway, I don't even remember where I was. Okay, so we multiply these together. This is going to go away because this is our conversion factor. And what will become our V1 ultimately is this number with a lot of decimal places. So we'll just simplify it to approximately 21.1 gallons. So what is that 21.1 gallons? Well, first of all, I have 6-gallon jugs. I have a lot of these, and these hold water for when we go up to the cabin and stuff like that. So we can have a pump and wash our hands while we're up there and things as such. Oh, he's knocking stuff down here. But anyway, those are 6-gallon capacity. And so this 21.1 gallons would fit about 3.5 of those. Right here is how you can approximately see that. And I have the gallons there for you. So that looks about the size of the sandstone block in rough comparisons. We know we're pretty close. All right, so we have 21.1 gallons as our new V1, which is less than 50 gallons. So we can safely put the sandstone block into our pond, which currently has 750 gallons in it, and we're only going to displace about 21.1 gallons of water. So 750, just to show you, plus 21, about 771.1 gallons. So we're still way under that 800. So that's another way to cross-check to see if it is fine to just set our sandstone block in. We're almost done. So our third and final question that we've taken from our story problem, we want to know if the porosity will significantly lighten the weight or reduce the mass of our sandstone block. And that was given to us in that USGS publication from the Dolomitic Mount Simon sandstone at 0.7%. Now, I'm just going to use the P for that. Now, those of you that know percent is a fraction of 100, okay? But we don't, when we calculate, we don't generally mess with the 100%. It's wonky and it's really unitless. So we just set it to 1. And in this case, I'm using 3 zeros for a reason. You'll see significant figures and all, but just for demonstration purposes. So 0.7% is equal to 0.007. That's why I included the zeros by the 1 up there. Okay, so you have this number. What do? Well, I'm just going to multiply it by kilograms. I decided to use kilograms instead of the grams because I don't want the numbers to get just too many decimal places and wonky. So we're just going to use kilograms, and I'm not going to use standard. There's no need to. What you need to get out of this more than, you know, how much actual mass, like, can I picture how much mass is missing, is you need to get out of it the process of which side of the scale we're working on. Is this significant? So you don't need to be able to picture the physical amount. Like if this works out to be 1 kilogram, which is 2.2 pounds, you don't need to be able to picture that 2.2 pounds. You just need to know that 2.2 pounds or that 1 kilogram is missing, and that's small in relation to this large number. Okay, so we can't multiply this directly by this because this will give us a very small number, which will work. That will give us the amount of missing mass or weight in our sandstone block. But that's not going to help us. What we want to know is, out of our calculated mass using this density, if we remove 0.7%, is that going to lighten our load significantly to where we can manage it easier? So what we need to know is the original mass here, but we just need to chip this little bit off, 0.7%. So what we are going to do is, there's a couple ways to attack this, but the easiest way is to take this percentage, this number, and this is our 1, and we just subtract it. I'm not going to set up equations for you or anything here. It's not necessary, although I could. And we get 0.993, which if we turned into percent would be 99.3%, would be left of our initial mass if we chipped off a 0.7% block. So that's what we need to know. We need to know that that is how much mass is going to be left if we chip off this. Okay, so what do? We just multiply this by this. Okay, so we multiply these two together. No units are going to cancel. Our kilograms, there's nothing to cancel against it. And we are going to make this our M0, which is this number. I don't really need to do that. I just wanted you to know. So what we're going to do is we're just going to multiply this by this. I changed this to an M0 or an M initial because we're going to get M1. And the number we come up with when we multiply those two together, and if the cat stops knocking things off the table, is 213.1 kilograms. As you can see, that isn't much difference than here. It's about 1.5 kilograms difference. 1.5 kilograms is only about 3.3 pounds that we're losing by removing our 0.7% porosity. So the thing isn't going to be much lighter. Missing this much of weight isn't going to make our job any easier. To answer our third and final question is it does not significantly reduce the weight to make this job easier for us. So that's how we would calculate to see if our sandstone block is going to fit on our dolly, and it will. We have plenty of room. Will it fit in our pond? Yes. With the amount of water we had in there, will we have to remove any? No. Is our porosity going to significantly reduce our mass or weight? No, it's not. So we answered all our questions. It's September 15th, 2020, and the only reason why I'm mentioning that is because of the forest fires out west in California, Oregon, and things as such, and it's pretty bad. I know Australia got hit really bad at the beginning of this miserable year. This year is just horrible. But anyway, I want everyone to be safe. We are starting to see the effects here in Indiana. I took this picture yesterday of the sun setting, and here's some video footage of the sun, and you can look at it straight with your eyes. And this picture here was still about half an hour before sunset. The sun should not look like that at all. It should be a lot brighter. But anyway, just stay safe, everyone. I'm not going to address any political BS about it. Any political comments will be deleted. And some of us actually just want people to be safe and things to get back to some sort of normality. We're not here to play BS politics, okay? So I just want to say that. But anyway, I think that's it. Is that it, Blackie? You got anything to say to your fans? Oh, he has so many fans. So many. But anyway, I think that's it. If you have any questions or comments, please leave them below. And I hope you learned something. Oh, hey, buddy. You want to say hi?